Lecture 15, Math 141. Our task today is to wrap up Section 2.7. And in this class, this group of 23 brilliant young men and women, they will have their test tomorrow. We're not going to show you that on cable TV, and we're not going to show you that on the DVD, but they will be taking their test tomorrow. Pay attention. Other than folks in this class, if you are taking this course on cable TV, pay attention to your test date that's provided to you. And later semesters on DVD, pay attention to not only when your test is, but what material is covered by that, because it may not be what is covered for the students in this physical classroom right now. All right, let's wrap up 2.7. We have our old friend, point-slope form, which we have used in a variety of ways to this point in time, not only just for review, find the equation if you know a point, you know the slope, but now that we have this thing called the derivative, the f prime, or the slope of the tangent, or the instantaneous rate of change, the derivative at a certain point will occupy that position. That's not a mystery. If we're evaluating the derivative at A, then our point must be A. So in fact, our point must be A, comma, f of A. So this equation becomes, instead of y minus the given y value, well, we know what the given y value is. It's the f of A. Slope, well, we know what the slope is. It's the f prime evaluated at A. It's the derivative, slope of the tangent. And x minus the specific x value, well, it's got to be A if we're evaluating the derivative at A. So this becomes our kind of updated model now that we know what the derivative is. I think we can pretty much wrap up 2.7 by looking at this example, which kind of covers everything in the last couple of sections. Let's suppose that we have a distance, height, or position function. And I specifically chose a rational function. So we can look at that process and review that process. So, pardon?
It's the same one from a WebAssign problem.
It is a WebAssign problem? Mm-hmm. Now, has that WebAssign already been due?
Yes.
Yeah.
Oh, well, shoot. Well, I don't know what, I guess that's where I got it then. We want the v of 2. So if this is a distance, height, or position function, and the units don't necessarily have to be provided, we don't know if s of t is in feet or meters or yards or miles or whatever. We don't know if t is in seconds or days or years. You don't have to know. Can't tell our units if we don't know, but we can at least evaluate the numerical value. So the v of 2, how do we start with the s function and end up being able to find the v of 2? Derivative. So we need this thing called the derivative. Don't make it more than it is. It's a slope. That's all it is. It's a slope on this curve at a specific instant. So it just so happens that the instantaneous rate of change of distance with respect to time is velocity. Once we get velocity, then we'll just plug to it, right? And it'll give us what we want. So we have a test tomorrow, so tell me what to write down here. This is our method, by the way, for test 1. We don't have any shortcuts yet. Limit as h approaches 0.
Like if we know the shortcuts, can we just check our work?
You can check your work with it. That's correct. Right. So you would have to show this work.
Okay.
And then if you know, for example, the quotient rule and or the chain rule, product rule, whatever you know, coming into this class, you're welcome to use it. But to get full credit, you need to go back to the definition of derivative at this point.
Yes.
So what's the numerator?
T plus H.
S of
T plus
T
H
plus H minus S of T all over H. Is that all right?
Yeah.
Mm-hmm.
It's not going to be a mystery now tomorrow on the test that a problem like this, it may not be an S of T, it might be a G of X or an S of Q or something. I mean, they're all the same, this kind of format. Difference of Y's, H is the difference of the, in this case, T values. You don't have to write that step down. You can go ahead and sub directly into the function itself if you want to. The S of T plus H, everywhere there's a T, it should be replaced with a T plus H.
H.
Does that look right?
Yeah.
Yes.
From that, we're going to subtract the S of T. All of that gets divided by H as H approaches 0. Next step, we're subtracting two fractions in the numerator. How does that get accomplished? Common denominator. Don't spend a lot of time searching for the least common multiple, which becomes the least common denominator, their product, right? Product of the two denominators. So I need to multiply this first fraction by what?
1 plus 2T.
1 plus 2.
Over itself, right?
Yes.
Yeah.
Which is really 1. And the second one needs to be multiplied by
1 plus 2T.
that thing over itself. This whole mess is divided by H. What's another way of accomplishing division by H?
Multiplied by 1 over H.
Multiplied by 1 over H. So there's the kind of the algebra that's set up for us based on a pretty simple concept that you probably learned in, I don't know, 5th grade, right? Putting two fractions together, getting that least common multiple, the least common denominator, and going from there. I don't think you had T's and H's in 5th grade, but the process was begun there. All right, so let's try to consolidate a couple of steps here if we can. Well, I don't know how wise that is. We're going to have this original numerator times this factor that we multiplied numerator and denominator by minus T so that's the numerator here minus the numerator here all over the common denominator. So that's kind of why we did that, is to put those two fractions together into a single fraction. And it all is divided by H, which we already converted to multiplication by the reciprocal. All right, T plus H, let's distribute that. What do we get? We're going to get a T plus an H. So we send it to the 1. Now let's send it to the 2T. What do we get? 2T squared plus 2TH. Does that take care of everything there?
Yes.
I think so. Everything that follows gets subtracted. So minus T minus T times 2T, which would be minus 2T squared, minus T times 2H. minus 2th. Does that look right? You do have some kind of checkpoints along the way. If you don't have a lot of terms kind of knocking each other out in the numerator, something probably went wrong. And then if you don't have everything that's left that has an h, then something probably went wrong, so you can go back and check your arithmetic. You can distribute across the denominator. It's not going to save you any time. In fact, it's probably going to waste some time, ultimately. I'm going to multiply by 1 over h by just putting the h in the denominator. All right, what do we lose in the numerator?
T.
Wait a minute. T minus t. 2t squared minus itself.
2T.
2th minus 2th. So is everything that's left, does it have an h in it?
Yeah.
In fact, that's the only thing that's left, right? Is h. So as long as h is not 0, h over itself reduces to 1. Always save the letting h approach 0 piece till the end of the problem. Which I think we're there now. So what happens to that as h approaches 0? 2 times the quantity t plus h. If h disappears,
Goes to 0.
then that just becomes, instead of twice t plus h, it becomes twice t, right? So the 1 doesn't change. Down here now we have 1 plus 2t, because the h disappeared, and another 1 plus 2t. So we have 1 plus 2t, the quantity squared. Anybody remember that solution from that web-assigned problem? So what do we want that for? What was the original question?
V and the V of T.
Okay, this is the v of t. I heard a couple things there. I heard that this is the v of t. We did want that, and we want that because we want the v of 2. Is that correct? So plug this into our new function, our velocity function. 1 plus 2 times 2. So for t, we plug in 2. There's 4 plus 1, 5 squared, 1 over 25.
Yep.
And we don't know the units because we don't know the linear units, feet, miles, yards, meters, nor do we know the unit time. So 1 over 25. Any part of that problem that you don't feel confident doing at this point in time? Probably going to ask you to do one somewhere in line with that tomorrow on the test. Certainly expect a rational function. If it's a polynomial, then that's a plus, right? Polynomials are easier. You just square binomials, cube binomials, that kind of stuff. Questions on that before it gets moved? I teach another class, and they took their first test yesterday, and one of the problems looked like this. Actually, it was just, there's no limit taking in this problem. This would just be like the slope of the secant, where we let h hang around in our final answer. H would be the change in x. So if I threw something like that on your test, cubing x plus h, What's that? I don't know that I'd go any higher degree than cubing for a polynomial, but
X cubed.
H cubed.
there is an h cubed. That's true. I'll put it out here where it belongs. Let's fill in the others.
One is
Plus.
Okay, there is an x squared h term. What's its coefficient?
H
3. 3 x squared h plus 3 x h squared. Is that it?
yeah.
That's it. It ought to have 4 terms because it was cubed. It's always one more than that. First term cubed here, last term cubed here. And you can use x's as they descend throughout, right? And the h's ascend throughout. H to the 0, h to the 1, h to the 2, h to the 3. So 4x cubed, 12x squared h, 12x h squared, 4h cubed. We're going to drop out the 4x cubed so we don't lose a lot here. 4x cubed minus 4x cubed, they knock out. Everything else has an h. $12x squared, 12xh, 4h squared. And as long as h is not 0, we can reduce those. So if this is all we're asked to do is to find the slope of the secant, then we're done, right? What if we wanted, question, Jonathan?
Would you assume that h is approaching 0 and kind of drop out those?
Well, now that's the next thing. So if we want h to approach 0, we're no longer talking about slope of the secant. We're talking about slope of the tangent. So it's really a different animal once we take the limit as h approaches 0. This has 2 points. It's got the first point, x, comma, f of x, and a second point, x plus h, f of x plus h.
So we would know what h is.
Right. Well, that or we just leave it alone and we allow for the fact that there is an h that's other than 0. So there's 2 distinct points for the slope of the secant. And that's good to have that question because that question then needs to be resolved, and it gets resolved by saying, how do I let these 2 points get closer and closer together so they're practically side by side and for all practical purposes the same point? You do that by letting h approach 0. So if h were to approach 0, how would it affect 12x squared?
No, wouldn't.
It wouldn't. How would it affect 12xh?
It'd make it go to 0.
It would diminish. The h would eventually take over, right? So this term would approach 0 because h itself is approaching 0. 4h squared also approaches 0. So if this were the slope of a tangent, the answer would be 12x squared. Now, let me resurrect the original problem that would lead to this. Here's the original problem. F of x equals 4x cubed. Here's the slope of the secant. Isn't that right? Isn't that the f of x plus h? There's the f of x all over h. So we're not going to let the limit, not going to take the limit as h approaches 0. Then we just stop there. So that's what we did. We stopped. And if we do allow the h value to get smaller and smaller and smaller, take the limit as h approaches 0. Now we no longer have 2 points, we have 1 point. Does that look like some of you, that many of you, most of you, know the shortcut? Is that the shortcut for the derivative of 4x cubed? 12x squared. It's a long way of getting there, but it gets there. Certainly not as bad as the rational functions. you will see some words in problems that might be new words for you in this section in 2.7. One of the words you might see is this word marginal. You might see it associated with cost. So if you are given a cost function and you want to know the marginal cost is the derivative of cost. So it's when we get some good examples where we're analyzing marginal cost, kind of on the margin, you kind of can predict what's going on along the curve by what's going on along the tangent to the curve. So we're kind of not using the curve, you're using a linear segment on the margin. Profit, if you are given a profit function and they are discussing P prime, or they ask you for the marginal profit. That word marginal is, to us, means that we need to find the derivative. It's the instantaneous rate of change. So you'll see that, and we'll deal with that in lots of examples from this point forward. All right, let's talk about some items. Anybody have a specific question that you're worried about this topic being on the test, and you want to resolve that in class today before tomorrow's test? Anybody? Any particular item? If you come up with something as we go through the rest of what we're going to do today in class, bring it up. Let's try to get it resolved.
Will you be asking us to find the inflection?
No inflection points, no places where the tangent line is horizontal. That's right around the corner, but we're not there yet. So let's say the f of x is this, and you are asked to find, and there's a purpose for this, the f of x minus the f of a all over x minus a. That's almost one of the definitions of derivative. One of our definitions of derivative is now, think about it for a second. For that to be the slope of a tangent, there isn't any h here. So what has to happen for this to be instead of 2 points? Good. X approaches a. So that's the kind of the alternate definition of derivative. You probably won't use that much, but if you were to use that, you certainly would have to know how to deal with that right there. That's not a derivative. This would be the slope of a secant, but you'd need to be able to do that to do this particular definition of derivative. So what would it look like? What's the f of x? I know that. 1 over x. That's my contribution. What's the f of a? 1 over a. Excuse me. So it's not meant to be a real complicated problem. Just kind of do what it says and then kind of go from there. What's next?
Multiply by 1 over.
Okay. Get a common denominator. So that's going to be multiplying by a over a and what? X over x. A minus x, right? All over ax. And that is, let's actually just write it this way this time. I don't like complex fractions. Hopefully you have a need like I do to get rid of them as soon as you have them. In fact, I want to get rid of it right now. How do you rewrite division by x minus a. Multiply by 1 over x minus a, right? Same way we did with division by h. We multiplied by 1 over h. So it kind of starts out a pretty simple, innocent problem. And there's some interesting parts to it. How about a minus x and x minus a? Good. Reduces to negative 1.
Oh,
Is that believable?
yeah.
5 minus 3 over 3 minus 5, right?
Yeah.
Reduces to negative 1. Any two numbers, you reverse the order of the subtraction, you get the same numerical value with a different sign, right? So I can reduce this and this, again, as long as x is not equal to a. And it doesn't reduce to 1, but it reduces to negative 1. So the end result, negative 1 over ax. So this is from a test that I gave last spring. Question on that before it gets moved? Now remember, we've also had a lot of pre-calculus stuff leading up to this calculus. That's potential stuff for the test. So let's say we want to find f inverse if we are given the function. This looks very similar to one that we did in class. In fact, Kent, I think you asked this question one day. You asked a question on an inverse from WebAssign that was very similar to this, I think. How do we find the inverse? And then let's go ahead. There's a couple of other questions, too. I'll add those in. Let's find the inverse first.
Switch x and y.
Switch x and y. So f of x is really y, right?
Mm-hmm.
So now we're going on to the inverse. Switch x and y. What's next?
Solve for y.
Okay, we eventually want to solve for y.
Multiply by y plus 5.
Okay, let's multiply both sides by y plus 5 or just cross multiply. What's next?
Distribute the x.
Good. Now that we've kind of distributed everything, let's get all the terms that have y on one side. Minus 5x. Minus 3. Excuse me.
Take out a y.
It's in there x times. It's in there minus 2 times. Good. Divide by x minus 2. So there's f inverse. So finding it is certainly important. Now, what are some other questions that might be asked?
Domain and range.
Okay, good. Domain. What's domain of the original function?
Negative 5.
Good. All reals but negative 5. What's the domain of f inverse?
All
reals
but 2.
Good. X is an element of the reals. X cannot be 2. Now, if we needed ranges, isn't the domain of f inverse the range of f? Is that correct?
Yes.
And vice versa. So, because how does that happen? Because don't we just interchange x's and y's? That's how we went about solving for inverse. So the domain of f is the range of F inverse. Is that right? The domain of F inverse is the range of F. I think we've done enough of this. Can you pick off the horizontal asymptote from this?
5.
Two.
-5.
Negative 5.
-5 would be the vertical asymptote, right? In fact, that's why x can't be -5, because it's completely undefined in that vertical line. What's the horizontal asymptote?
2.
Y equals 2. And isn't that kind of what we said down here? That the domain of F inverse becomes the range of F. Y equals 2 is a horizontal boundary, so that function probably will never take on the value 2. What's the horizontal asymptote down here?
Negative 5.
-5. That ought to look familiar, right, from the data that we've accumulated to this point. So that's part of what I really like and enjoy about math, is that things are connected. I can a lot of times pick up a mistake that I make later in a problem because I know what's supposed to happen and it's not happening. I know that the horizontal asymptote better be y equals 2. In essence, y can't be 2 because on the inverse, x can't be 2. So they kind of mesh with one another, which is, I think, makes math kind of interesting and unique.
Can you go over the horizontal thing? They get got the same coefficient?
Right. All right, so let's say we have a rational function, which we just used some shortcuts right there. Let's say that the rational function looks like this. And we want to know the horizontal boundary, horizontal asymptote. So in essence, what we really want is we want to know what happens to this function way out there to the right somewhere, right? X approaches infinity. So isn't the title of one of the sections of this material limits involving infinity, right?
Yeah.
So this is potential test stuff. Now the shortcuts, well, we'll get to the shortcut in a second. What should work if you draw a blank on the shortcuts? You forget the shortcuts.
Divide by the highest degree of
Good.
denominator.
Divide through by the highest degree of x that you see in the problem. So we would divide everything by x squared, right? See what happens as x approaches infinity. Or, if you remember the shortcut, what is it in this case where the degree of the numerator is smaller than the degree of the denominator?
It's a ratio.
Approaching 0.
0, right?
The denominator is getting infinitely larger.
Much faster than the numerator. Numerator's getting large, but the denominator's getting larger faster. When that happens, the value of that fraction approaches 0. So if we were looking for a horizontal asymptote up here, we would say y equals 0, right? For that rational function. Another rational function. We were searching for an asymptote, horizontal asymptote.
At 1.
Way out there to the right. So this y value eventually approaches what number as x gets tremendously large? 5 halves. So the shortcut is same degree,
Coefficient.
right? Numerator and denominator. It's the quotient of those lead coefficients. And then the third case, there's only other one case. That's where the degree of the numerator is larger. What happens
Doesn't
there?
have a limit.
It doesn't have a limit. So therefore, it wouldn't have a horizontal asymptote, a linear horizontal asymptote. Okay. Continuity. You check for continuity at an individual x value. Is a curve continuous somewhere specifically at x equals a? What's the first thing you check for if you're trying to determine if a function is continuous at x equals a?
There's a point.
Okay, there's a point plotted there. So does the f of a exist? Or, better, the question is there a point plotted there? So if there is a point plotted there, a is 2, and 2 is paired with 5, so 2, 5 is plotted. Then we go on to test 2. If it fails there, what's our conclusion? Discontinuous. Okay? If there's not a point plotted there, it cannot be continuous. Okay? If it gets by checklist point number 1, what's number 2? Okay? The limit exists on this function as x gets closer and closer to a. So are we converging on this same value from both sides? Right? What value? Well, hopefully the same value from part 1 that was actually plotted. So let's say the limit exists. So then we would go on. If the limit does not exist, meaning we're not converging on the same value from both sides, then we're done. It's discontinuous. So we did plot a point when x is a. It does have a limit. And in order for this to actually be continuous, what's the final conclusion we have to be able to draw?
They have to be equal.
They're equal to each other. So this y value that was actually plotted is, in fact, the limit that we approached from both sides. So if that is true, then it is continuous. And if you think about that, it has to be continuous. You're converging on the same value that was actually plotted. The only way that could be is continuous. And if that doesn't happen, the only thing that could be is discontinuous.
Wait, so for this in the test, is there going to be like a picture that we're
Yes.
going to have to look
Or
at?
you might come up with a picture. So let's say that I had, and here's an example from this test that was given last spring.
Will it be freaky?
It'll be pretty, but it won't necessarily be.
Did you ask us to like draw one that isn't continuous or something?
Yeah, it's possible that the picture we draw could be continuous at a certain value, and it could actually be discontinuous at a certain value. And then that lends itself to one-sided limit questions and things like that. So
But it'll be a pretty picture.
be pretty. So this split domain function happens to be 3 pieces. That's a constant, that's linear, and that's linear. So none of the 3 pieces are, really cumbersome. It's just a matter of taking care of where do we start and where do we stop in terms of the domain. Does anybody have a graphing calculator that you can enter in a split domain function and it plots it for you?
Can't use it.
I've never seen one. So those are wonderful machines, but we also need to know how to plot points ourselves.
Can we use a calculator now?
Yeah, you can use a
Oh, we can.
calculator. I mean, I would recommend bringing a scientific calculator at least that does exponentials, trig, and logarithms. I mean, those are kind of necessary. If you also have a graphing calculator, that's fine. I don't really think a graphing calculator is going to help you too much on this problem because you're not going to be able to kind of stop and start it with the different pieces of the domain. But if problem on the test asks you to graph, then that means your graphing mode is off limits for that problem. That really comes into play more on the next test. All right, so let's take the 3 lines of this. There's the first line. Y equals 1, x less than or equal to -1. So I can put in -1, right, and include that point, and -2, and -3, and we could do more, but these are lines, so we don't need to do a whole bunch. What is the y value in each case?
1.
1. So that point is included because x is less than or equal to -1. On this one, I'm really not supposed to use -1. I'm going to put it in there anyway. If x could be -1, what would be the y value in this middle line? -1?
Yes.
Okay, and I'm going to remind myself to delete that point. I want to come right up next to that point, but do not include it. X can be 0, 2, and we're really not supposed to use x equal to 1, but I'm going to put it in here anyway. And if x could be 1, y would be 5, but that point is deleted. Open circle. 1 or larger. Now we go to the third line. So I can put in 1 if x can be 1, which it can be. What is y?
5.
5. If x could be 2, 3, and that's enough. It's linear. Everybody okay with just the point plotting? So let's try to take these points. So -1, 1, -2, 1, and so on. -1, -1 is an open circle. 0, 2 is included. And 1, 5 is an open circle. Linear. Let's use our imagination there. Mine doesn't look all that linear. And the next one, 1, 5. Now, I specifically wanted the point that was deleted here to actually be included here. So if it's been deleted from one piece and included in the other piece, either it's part of the set or it's not. Is it part of the set? It is. So we fill that in because of the next piece. And then 2, 3 is included. So I've got a couple things, and this is purposeful on this problem that I gave on the previous test. I've got a discontinuity going on here at -1, but I've got a continuity going on here at 1. So it kind of depends which piece of the graph we're looking at. Now, I used -1 here on this graph on my questioning for this test. So let's use that one, because we know it's discontinuous there. It's going to fail at one of these places. First checkpoint for continuity.
Is there a point there?
Is there a
No.
point plotted when x is -1?
Yes.
Yes. -1, what? 1?
Yeah.
So, at least as far as that test is concerned, it appears to be continuous. We know better. Second piece.
A limit.
Okay, limit as x approaches -1. I guess we could look at this in pieces, right? As x approaches -1 from this direction, what's the y value approaching? 1. As x approaches -1 from this direction,
-1.
negative 1. So does it have a limit as x approaches negative 1 from both sides?
No.
No. Does not exist. So therefore, it's discontinuous. And if it had passed that test, was our answer to part number 1 the same as the answer to part 2? If it is, then it's continuous.
Do you have to like go through it like that? Because if you just look at the graph, you could just say, obviously, it's discontinuous.
Well, you do have to say at some point that the limit doesn't exist
Right.
from both sides.
Okay.
If you say where it fails, then even though it may have passed or failed the first test, if it fails anywhere, it's discontinuous, right? So if a point's not plotted there, end of problem. If the limit doesn't exist from both sides, you're done. Probably 2 more examples. Let's show that there's a root of this function in the interval from 1 to 2. So a root means it crosses the axis, right? Crosses the x-axis. A 0 is another term for this. How would you go about that? Okay. Plug in 1. What's the f of 1? Negative 1. What's the f of 2?
Gene.
15? 15, right?
Yeah.
Now, the simple fact that we got a negative here and a positive here, does that mean that this has to cross the axis
Yes.
as we
Yes.
connect the point 1, negative 1 to the point 2, 15?
Yes.
We better justify something, though. Only if the function is
Continuous.
continuous. So if the function is continuous, so we better write that down because that's part of the package here. Is it continuous? Yes. Why is it continuous? What is that?
It's a polynomial.
That's a polynomial. So it's a polynomial, which means we have to be able to connect this dot to this dot. How do you connect that dot to that dot without crossing the axis? You don't. You do have to cross the axis. So by the intermediate value theorem, does that ring a bell? If it doesn't, look back at that. We didn't talk about it a long time, but we did address it in this class. By the intermediate value theorem, f of x must be 0 as x goes from 1 to 2. You can't go from negatives to positive without being 0 if the curve is continuous. But this is part of it. You do have to address continuity. If it's not continuous, it doesn't have to be true. Everything else I see here we've done like within the last 3 days, so I think we're good on that. Test tomorrow. We don't know it, and you wouldn't be expected to solve it. Let me, before everybody leaves, if you want to start a few minutes early, like if you want to, instead of start at 10:15, you want to start at 10:10, I'll be here. You get those 5 extra minutes, and then 5 minutes at the end of class if you need those, so you'll have a full hour.